Look up at the stars tonight, and what you see is just a fraction of the cosmic puzzle. 95% of the universe remains hidden in shadows, dark matter weaving through space, black holes warping reality, and forces we can't even name. These aren't just scientific curiosities. They're the unsolved mysteries that keep astrophysicists tossing and turning at 3 in the morning. Why does the universe seem to play by rules we can't decipher? What does the eerie silence of the cosmos tell us about our place in it? These questions don't just challenge our textbooks, they rewrite them. Today, we're diving into the greatest enigmas of the cosmos, the ones that stretch our understanding to its limits. By the time we're done, you'll see the night sky not just as a collection of stars, but as a frontier of unanswered questions waiting to be solved. Picture this, a universe so vast it holds more stars than grains of sand on every beach on Earth. With numbers like that, intelligent life should be everywhere. So why does space feel so empty? This is the Fermi Paradox, a puzzle that's haunted scientists since the 1950s. Physicist Enrico Fermi first posed the simple but devastating question: if the universe is teeming with potential, where is everybody? Statistically, we shouldn't be alone. Yet after decades of scanning the skies, we've heard nothing but silence. Some think civilizations might hit a self-destruct barrier, wars, climate collapse, or runaway technology wiping them out before they can reach the stars. Others argue that advanced life could be so different from us, we wouldn't even recognize their signals. Maybe they've moved beyond radio waves or they're hiding. Or worse, could we be the first? The unsettling truth is we still don't know. Every silent hour of telescope data deepens the mystery, leaving us to wonder, are we the exception, or is the universe keeping its greatest secret just out of reach? Here's something that will bend your mind. Everything we can see, touch, and measure, from distant galaxies to the screen in front of you, makes up less than 5% of the universe. The rest, a ghostly presence we call dark matter. Think of it like the invisible hand shaping the cosmos, bending light around galaxies and holding them together with gravity we can't explain. It doesn't shine, it doesn't cast shadows, yet without it, the universe as we know it wouldn't exist. For decades, scientists have chased this phantom, running experiments in underground labs and smashing particles at near light speeds, hoping for even a flicker of evidence. Some believe dark matter could be made of undiscovered particles, something entirely outside the known laws of physics. Others wonder, what if we've got gravity all wrong? What if, instead of invisible matter, our equations are missing something fundamental? Every time we think we're close, dark matter slips through our fingers. Galactic rotation curves don't match predictions. Light bends in ways it shouldn't. Entire clusters of galaxies move as if tugged by something unseen. The deeper we look, the more questions pile up. Will we crack this cosmic code, or is the universe playing a game we're only beginning to understand? One thing's certain until we solve it: dark matter remains the ultimate cosmic hide and seek. If dark matter is the invisible glue holding galaxies together, dark energy is its bizarre opposite, the unseen force ripping the cosmos apart at the seams. Imagine blowing up a balloon with tiny dots on its surface. Now, imagine the balloon starts inflating faster and faster, the dots racing away from each other. That's our universe right now, accelerating in every direction, and dark energy is the cosmic breath behind it. What makes this so unsettling? Unlike gravity, which tugs matter inward, dark energy operates on empty space itself, stretching the very fabric of reality. Einstein briefly flirted with the idea, calling it the cosmological constant, only to dismiss it as his greatest blunder. Turns out he might have been onto something. When astronomers discovered this runaway expansion in the late 1990s, it shattered expectations. the universe wasn't just growing, it was speeding up. Is dark energy constant, or does it evolve over time? Could it grow stronger, tearing atoms apart in a big rip, or fade away, leaving the cosmos to collapse? Right now, we have more theories than answers. Some suggest it's a property of space itself, a sort of anti-gravity woven into the universe's blueprint. Others wonder if entirely unknown physics are at play, something beyond our current equations. One thing's clear: dark energy controls the ultimate fate of everything. Will the cosmos end in icy isolation or violent disintegration? Until we crack this riddle, the universe keeps expanding its secrets faster than we can chase them. At the heart of our galaxy lies a monster, a supermassive black hole with gravity so intense it twists the laws of physics into knots. These cosmic enigmas don't just swallow light, they bend reality itself, creating a point of no return called the event horizon. Step beyond it, and the universe as you know it ceases to exist. But here's the twist: black holes might not be the cosmic trash compactors we once thought. Quantum mechanics says information can't be destroyed, yet black holes seem to erase it completely. Stephen Hawking threw this contradiction into sharp relief, suggesting black holes slowly evaporate, leaking mysterious Hawking radiation. But if they fade away, where does all that trapped information go? Some physicists argue it scrambled and eventually returned, like a shredded document reassembled by quantum forces. Others propose something wilder: that black holes are portals, birthing entirely new universes inside their depths. Then there's the eerie silhouette captured by the Event Horizon Telescope. Those haunting images revealed unexpected structures, like glowing photon rings dancing just outside the abyss. Why do they form? What secrets do they hold? Every answer we uncover spawns 10 new questions. From their paradoxical cores to their mysterious outer ripples, black holes force us to rewrite physics itself. Are they cosmic destroyers or gateways to realms beyond our imagination? Until we peer deeper into the darkness, their true nature remains one of the universe's most thrilling unsolved puzzles. We think of the Big Bang as the ultimate beginning, a moment when space, time, and matter erupted into existence. But here's the catch: if the universe was born from a single point of infinite density, what existed before it? The question isn't just scientific, it shatters our very notion of cause and effect. Time, as we understand it, might not apply there. Some theories paint a picture of a cyclic universe, where our Big Bang was just one heartbeat in an endless cosmic cycle: expansion, collapse, and rebirth. Others suggest a multiverse, with our universe bubbling up from a vast sea of other realities, each with its own laws of physics. But the wildest idea: that time itself didn't exist until the Big Bang, making, before, a meaningless concept. Physics hits a wall at the singularity, a moment so extreme our equations crumble. Was it a quantum fluctuation in some deeper void, a collision of higher dimensional membranes, or something we haven't even imagined? Clues might lie in the faint afterglow of the cosmos's birth, the cosmic microwave background where tiny ripples could hint at conditions before time began. For now, the Big Bang remains the ultimate origin story with no prologue. It's a mystery that blurs the line between science and philosophy, leaving us to wonder: did the universe truly have a beginning, or are we just seeing one chapter in an epic far grander than we can comprehend? Somewhere beyond the Milky Way's glittering veil, an invisible force is pulling us and everything around us into its grip at breakneck speed. Meet the Great Attractor, a cosmic anomaly so powerful it bends the paths of entire galaxies like rivers flowing toward an unseen waterfall. Hidden behind thick clouds of interstellar dust, this gravitational mystery tugs at thousands of galaxies, including our own, dragging them toward a point we can't even see clearly. For decades, astronomers mapped this motion with growing unease. The Milky Way isn't just drifting, it's racing at over 1,000,000 miles per hour towards something colossal. Early theories suggested a supercluster of galaxies, a dense knot in the cosmic web. But when researchers peered through the dust with X-ray telescopes, they found Normal, the Norma cluster. A massive grouping of galaxies wasn't nearly heavy enough to explain the pull. So what's really out there? Some speculate the Great Attractor might be part of something even larger, a sprawling structure like the Shapley supercluster lurking farther in the distance. Others wonder if it's a sign of something stranger: exotic physics, unseen dimensions, or dark matter arranged in ways we've never imagined. Every new observation complicates the puzzle. Why does the pull extend so far? What's hiding behind the Milky Way's dusty curtain? One thing's certain: the Great Attractor forces us to redraw our maps of the universe. It hints at hidden giants in the cosmic dark, structures so vast they reshape our understanding of gravity itself. Until we pierce that obscuring veil, this enigmatic force will keep pulling us not just through space but deeper into the mystery. Out of the blackness between galaxies comes a flash brighter than 1,000,000,000 suns, lasting less than the blink of an eye. These are fast radio bursts, some of the most explosive and mysterious signals in the universe. In mere milliseconds, they release enough energy to power our entire civilization for centuries. But what's causing them? The possibilities range from the spectacular to the spine-tingling. First detected in 2007, these bursts arrive from billions of light-years away, often with no warning. Some fire once and vanish forever. Others repeat in strange, unpredictable rhythms like a cosmic heartbeat. One source even follows a steady 16-day cycle, on, off, on again, as if programmed. That kind of precision sends chills down astronomers' spines. Could these be natural, or is something, or someone orchestrating them? The leading theories are dramatic enough: colliding neutron stars, magnetars, highly magnetic dead stars snapping like overloaded rubber bands, or even evaporating black holes emitting dying screams. But the repeating patterns don't always fit. Some bursts show signs of passing through dense magnetic fields, suggesting bizarre environments unlike anything we've seen. Then there's the wild card: what if these are technosignatures, enormous alien transmitters, interstellar beacons, or even the leakage from unimaginable energy projects? The truth is, we're still catching these bursts by accident, like overhearing fragments of a conversation in a language we don't understand. Every new detection adds another piece to the puzzle. One thing's certain: fast radio bursts remind us how much we still don't know. Whether natural cataclysms or cosmic engineering, they're a reminder. The universe is stranger, louder, and far more unpredictable than we ever imagined. Take a deep breath, because this next cosmic oddity might make you question everything we think we know about the universe's symmetry. When scientists mapped the cosmic microwave background, the faint afterglow of the Big Bang, they expected a random, uniform scatter of hot and cold spots. Instead, they found something baffling: an eerie alignment across the sky so unsettling, researchers called it the axis of evil. Picture throwing confetti into the air, only to watch it arrange itself into unnervingly straight lines. That's roughly what the CMB does. The temperature fluctuations don't just vary randomly, they seem to follow a preferred direction, almost as if the universe itself has a hidden axis. This shouldn't happen. According to the cosmological principle, the universe is supposed to look the same in all directions. No special spots, no cosmic north. Yet the data screams otherwise. Could this be a fossil from before the Big Bang? A scar left by some primordial structure that predates time? Or is it just an illusion, a statistical mirage in the noise? Skeptics argue it might vanish with better measurements, but after 2 decades of refined observations, the signal persists. Some theorists whisper about exotic possibilities, a universe shaped by unseen forces, or even evidence we're embedded in something far larger, a multiverse imprinting its geometry onto ours. The unsettling truth: if the axis of evil is real, it means the cosmos might not be as indifferent or uniform as we thought. There's a whisper of order in the chaos, a fingerprint on the universe's blueprint we can't yet decipher. Whether flaw or clue, one thing's certain: this anomaly keeps physicists up at night, rewriting their models and wondering, what else have we gotten wrong about the grand design of reality? Einstein's general relativity paints gravity as the curvature of space-time, a cosmic dance where planets and galaxies bend the fabric of reality. Meanwhile, quantum mechanics reveals a chaotic subatomic world where particles pop in and out of existence, governed by uncertainty. Here's the problem: when you try to combine these two titans of physics, the math explodes into nonsense. Black holes highlight this feud perfectly. Their immense gravity crumples matter into an infinitely dense singularity, a point where relativity's equations fail and quantum mechanics throws up its hands. This isn't just a scientific inconvenience, it's a glaring sign that our understanding of reality is incomplete. Efforts to unite these theories have spawned mind-bending ideas. String theory suggests everything is made of tiny vibrating strings, with gravity just another note in their symphony. Loop quantum gravity imagines space-time as a web of interconnected loops, pixelating the smooth canvas Einstein described. But here's the catch: none of these theories have experimental proof. They're mathematical masterpieces without a gallery to hang them in. Even the most brilliant minds, from Hawking to Penrose, have wrestled with this divide, leaving us with paradoxes instead of answers. Why does this matter? Because without quantum gravity, we can't fully grasp the birth of the universe, the fate of black holes, or even the true nature of reality itself. It's like trying to read a cosmic instruction manual with half the pages ripped out. Every failed experiment or unexpected observation, like Hawking radiation or holographic principle hints, offers tantalizing clues. But the grand solution, still out there, waiting for a genius to stitch the universe back together. Until then, this rift between the very big and the very small remains one of physics' greatest unsolved challenges. Deep in the void between planets, two robotic pioneers were caught in a cosmic whodunit. As Pioneer 10 and 11 raced toward the outer solar system, something strange happened. They began slowing down just a fraction more than Newton's laws predicted. At first, it seemed trivial, like a car losing speed on a slight incline. But over decades and billions of miles, that tiny discrepancy grew into one of spaceflight's most perplexing mysteries. Engineers checked every possible culprit: fuel leaks, solar wind, even pressure from the spacecraft's own radio signals. Nothing explained the deceleration. For years, whispers swirled about unseen matter tugging at the probes, or worse, that gravity itself behaved differently in the icy reaches of the solar system. The numbers didn't add up, and for a while it looked like we'd stumbled upon a crack in physics itself. Then came the twist. Meticulous analysis revealed a far more mundane suspect: heat. Not from the sun, but from the spacecraft's own electronics, radiating off in uneven bursts. Like a tea kettle whistling steam, that thermal push was enough to alter Pioneer's trajectory ever so slightly. Case closed, not quite. While heat explains most of the anomaly, some researchers still spot tiny irregularities in the data, ghosts of a puzzle that might not be fully solved. The Pioneer anomaly reminds us how even the quietest corners of space can unsettle our understanding. Sometimes the universe hides its secrets in plain sight, not in dramatic bursts of light, but in the faintest whisper of warmth against the infinite cold. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a blast of noise so unusual it made an astronomer scrawl, "Wow." In the margin of the printout, for 72 seconds, this signal surged 30 times louder than the cosmic background noise, then vanished without a trace. Decades later, it remains astronomy's most tantalizing ghost, a cosmic shout in the dark that no one has ever heard again. The signal fit perfectly into the expected frequency band where hydrogen, the universe's most common element, emits natural radio waves. But here's the catch: hydrogen doesn't flare up like that on its own. The pattern suggested an artificial origin, like a deliberate transmission beamed from deep space. Skeptics argue it could have been a rogue comet's reflection or an earthly signal bouncing off space debris. Yet none of those explanations fully fit. The frequency was too clean, the timing too precise, and the source location too empty. Then there's the eerie silence. After years of scanning the same patch of sky, not a single blip has echoed that original hello. Was it a one-time glitch, an alien beacon flickering past Earth's telescopes, or something even stranger we haven't considered? The harder we look, the more the wow signal slips through our fingers. Whether a fleeting natural anomaly or the universe's most cryptic postcard, one thing's clear: it's proof that the cosmos still has surprises up its sleeve. Every unanswered signal is a reminder we might not be alone, but the universe isn't giving up its secrets easily. We think we know what the universe is made of: stars, planets, and swirling galaxies lighting up the darkness. But here's the shocker: even the ordinary matter, the stuff we should see, is playing hide and seek on a cosmic scale. According to the Big Bang's playbook, there's a specific amount of baryonic matter. Protons, neutrons, the building blocks of everything familiar that has to exist. Yet when astronomers tally it all up, half of it is simply gone. So where does an entire universe's worth of matter vanish? The leading suspect: an invisible web of superheated gas stretching between galaxies like ghostly threads. Imagine steam so thin it's practically undetectable, woven through the vast cosmic voids. These filaments, predicted by simulations for decades, could hide enough missing matter to solve the puzzle, if only we could spot them. The challenge: this gas isn't cold and clumpy like the clouds we're used to. It's scorching, ionized, and barely dense enough to register. Traditional telescopes can't see it. The gas doesn't glow brightly or block light passing through. But clever workarounds are emerging. By studying how distant quasars dim as their light passes through these filaments, or hunting for faint X-ray whispers from the gas itself, astronomers are finally piecing together the trail. The takeaway: even the ordinary universe is full of surprises. If half the matter we take for granted is hiding in plain sight, what else are we overlooking? Every new detection method brings us closer to solving this cosmic shell game, and reminds us just how much of reality still slips through our nets. Here's a cosmic detective story unfolding in real time, one where the clues don't add up and the universe might be hiding something fundamental. Astronomers have two ways to measure how fast the cosmos is expanding: by studying nearby stars and galaxies, or by analyzing the ancient glow of the cosmic microwave background. Both methods are precise, both are backed by mountains of data, and yet they give stubbornly different answers. This mismatch isn't just a rounding error. It's a full-blown crisis dubbed the Hubble Tension, and it's shaking the foundations of modern cosmology. Think of it like two clocks: one, built by observing pulsating stars called Cepheids and exploding supernova, ticks steadily, telling us the universe's current expansion rate. The other, based on the CMB, the faint echo of the Big Bang, operates like a fossil, revealing how fast the universe should be growing based on its infancy. But these clocks are out of sync by nearly 10%, a gap that grows wider with every new observation. The implications: either we've misread the cosmic yardsticks or something stranger is at play. Could dark energy, the mysterious force accelerating expansion, be changing over time, stronger today than in the ancient universe? Are there undiscovered particles warping the early cosmos, throwing off our CMB calculations? Or, most tantalizing of all, is this a hint of entirely new physics, a cosmic rulebook we haven't cracked yet? The Hubble tension isn't just academic. Resolving it could mean rewriting textbooks, revealing hidden forces, or uncovering flaws in Einstein's framework that only appear at cosmic scales. Every new telescope, from JWST to upcoming dark energy surveys, is racing to solve this puzzle. Until they do, the universe keeps whispering our uncomfortable truth. Our map of reality might be missing whole chapters. Imagine taking every book, every memory, every piece of reality you've ever known, and shredding it into particles so tiny they vanish without a trace. That's the nightmare scenario at the heart of black holes, where Einstein's relativity and quantum mechanics collide in a fiery paradox. According to quantum rules, information, the fundamental code of the universe, can never truly be destroyed. Yet black holes, with their crushing gravity and inescapable event horizons, seem to break this law daily. Here's the problem: when matter falls into a black hole, it's stretched, compressed, and ultimately lost beyond the point of no return. Stephen Hawking's groundbreaking work showed that black holes aren't eternal. They slowly leak energy, evaporating over eons. But if a black hole vanishes, where does all that swallowed information go? Quantum physics insists it must still exist somewhere, scrambled beyond recognition, perhaps, but never erased. Possible solutions sound like science fiction. Some theorists suggest black holes spit the information back out via Hawking radiation, like a cosmic printer reassembling shredded documents from smoke. Others propose holographic universes where all the lost data is encoded on the black hole's surface, a 2D vault preserving 3D reality. The wildest ideas invoke alternate dimensions or baby universes birthing inside the singularity, carrying away the secrets we thought were lost. Yet none of these theories fully satisfy both quantum mechanics and general relativity. The math still clashes, leaving physicists in a stalemate. Every new calculation either deepens the mystery or exposes another flaw in our understanding. Are black holes the universe's ultimate shredders, or are we missing a fundamental piece of the puzzle? This paradox isn't just academic, it's a battle for the soul of physics. If information can disappear, our most trusted laws crumble. If it can't, then reality hides mechanisms we've yet to imagine. Until we crack this riddle, black holes will remain cosmic enigmas, challenging us to rethink existence itself. Our moon seems so familiar, a silent companion hanging in the night sky. But buried in its ancient rocks lies a secret that defies everything we know about planetary magnetism. Samples brought back by Apollo astronauts revealed something astonishing. The moon once had a magnetic field rivaling Earth's, strong enough to shield its surface from solar winds. Here's the puzzle: our magnetic field comes from Earth's churning liquid iron core, a cosmic dynamo constantly in motion. Yet the moon's core is tiny, mostly solid, and far too small to power such a force. So how did it generate this planetary strength shield billions of years ago? Some scientists point to cataclysmic collisions, giant asteroids slamming into the moon so hard they stirred its core like a spoon in molten metal, jump-starting a temporary magnetic engine. Others argue tidal forces might be the key. As the young moon flexed under Earth's gravitational pull, friction deep inside could have heated its core enough to spark magnetism. But there's a catch: these explanations only account for brief bursts of activity, not the sustained field hinted at in lunar rocks. Then there's the wild card: what if the moon's interior was radically different back then? Maybe it harbored a dense, swirling layer of molten metal we've never detected, or its rotation created currents we can't replicate in models. Each theory has gaps, leaving researchers chasing shadows in the data. The more we study those ancient Apollo samples, the clearer it becomes the Moon's magnetic past is a locked door, and we're still searching for the key. This isn't just about lunar history, it challenges our understanding of how rocky worlds generate magnetic fields at all. If something as small as the Moon once rivaled Earth's magnetism, what other surprises might hide in the cosmos? Every unanswered question reminds us, even our closest celestial neighbor keeps secrets we've yet to uncover. Out past Neptune's icy orbit, where sunlight is little more than a faint glimmer, lies a cosmic puzzle waiting to be unraveled: the Kuiper Cliff. Picture the outer solar system like a vast construction site, with debris left over from its formation scattered across the Kuiper belt. But here's the odd part: instead of tapering off gradually, this belt of icy objects comes to a jarring, almost unnatural stop. It's as if someone drew a line in the cosmic sand and said, "This far and no farther." What could cause such a sharp boundary? One compelling idea points to an unseen world lurking in the dark, a hypothetical planet 9 with enough gravity to sweep the area clean beyond a certain point. If it exists, this elusive planet could be yanking objects into new orbits or even ejecting them from the solar system entirely, leaving behind this eerie emptiness. But not everyone's convinced. Some researchers argue the Kuiper Cliff might be a cosmic mirage, an observational bias where faint, distant objects are simply too dim for our telescopes to spot. Others suggest the solar system's primordial disk of gas and dust might have had its own built-in edge, carving this boundary billions of years ago. Then there's the wild card: could something even stranger be at play? A passing star long ago stealing material from our system's fringe, a hidden population of stealthy, dark objects warping the belt structure. Every theory has gaps, and every new survey deepens the intrigue. The Kuiper Cliff isn't just a curiosity, it's a challenge to our understanding of how planetary systems evolve. Whether it's a hidden architect or a flaw in our models, one thing's certain: the solar system's outer limits still hold secrets we've only begun to uncover. Among the countless stars dotting our galaxy, one shines, or rather, flickers like no other. Meet KIC 8462852, better known as Tabby's star, a cosmic oddity that doesn't just twinkle, it plunges into darkness without warning. Imagine a light switch flipping on and off at random, dimming by as much as 22% before brightening again. Planets can't block that much light. Even Jupiter, our solar system's giant, would barely make a dent. So what's casting these colossal shadows? When astronomer Tabetha Boyajian first spotted this bizarre behavior in 2015, the explanations ranged from plausible to downright fantastical. A swarm of comets, perhaps, a massive family of them, trailing dust clouds thick enough to blot out the star's glow. The problem: that would require more comets than we've ever seen in one place, thousands upon thousands, all moving in sync. Others pointed to interstellar debris, a rogue band of cosmic clutter drifting across our line of sight. But again, the numbers don't quite add up. Then came the idea that set the internet ablaze: alien megastructures. Specifically, a Dyson swarm, a hypothetical network of energy-harvesting satellites built by an advanced civilization to encase their star. It's a thrilling thought, but here's the catch: after years of scrutiny, no telltale signs of technology, like laser emissions or heat patterns, have surfaced. Even the star's own light, when split into colors, doesn't match what we'd expect from artificial constructs. So where does that leave us? Newer studies suggest uneven dust clouds, finer than smoke particles, might be the culprit, natural, yet just irregular enough to defy easy explanation. But skeptics note even this theory can't account for the star's long-term, gradual dimming over the past century. Tabby's star is a reminder that the universe loves a good mystery. Whether it's cosmic dust or something far stranger, This flickering enigma keeps us guessing and proves that sometimes the most ordinary-looking stars hide the wildest secrets. Stretching over 1 billion light-years across the constellation Eridanus lies a cosmic nothingness so vast it defies explanation. This isn't just an ordinary void between galaxies, it's a staggering abyss, a region of space where matter seems to have been scrubbed away on an unimaginable scale. But here's where it gets weirder. This gaping emptiness aligns perfectly with one of the coldest spots ever detected in the cosmic microwave background, the faint afterglow of the Big Bang. That chill shouldn't be there, not unless something colossal warped the fabric of reality itself. At first glance, the cold spot could be written off as a statistical fluke, a random dip in the universe's thermal fingerprint. But paired with the supervoid's eerie presence, scientists can't help but wonder, did something happen here? One radical theory suggests this might be the scar of a cosmic collision, a bruise left behind when our universe brushed against another in the multiverse. Imagine two soap bubbles grazing each other in some higher dimensional space, their membranes exchanging energy in a fleeting encounter. The result, a pocket of stretched, drained space-time, and a chill in the cosmic background we're still feeling billions of years later. Skeptics argue the cold spot and the void might not even be connected, that their alignment is pure coincidence in an already lumpy universe. Yet simulations struggle to produce such a stark emptiness naturally. If the void truly is responsible for the cold spot, its sheer size would require exotic physics, something beyond our standard model of cosmic evolution. Could it be evidence of dark energy behaving strangely, or a remnant of quantum fluctuations from the universe's first moments? Every new observation deepens the intrigue. Some researchers are now hunting for subtle distortions in the light passing through the void, hoping to catch traces of whatever carved this cosmic crater. Others are refining models to see if multiple smaller voids could mimic the effect. But if the Eridanus Supervoid is what it appears to be, a single, incomprehensible emptiness, it forces us to confront a humbling possibility: that the universe still holds phenomena we haven't even begun to imagine. Whether it's a window into the multiverse or just a freak of nature, one thing's certain: this cosmic cold spot is more than a curiosity. It's a crack in the foundation of our understanding, reminding us that even the emptiest corners of space can hold the universe's most profound secrets. Galaxies aren't supposed to break the rules, but NGC 1052 DF2 isn't playing by them. Imagine a cosmic rebel so strange, it shouldn't exist according to everything we know. Most galaxies are like ships held together by invisible ropes. Dark matter's gravity binds their stars in place, but this one, it sails through space almost completely untethered, its visible stars moving at speeds that make no sense without dark matter's hidden hand. When astronomers first measured its rotation, the numbers sent shockwaves through the astrophysics community. Stars in NGC 1052 DF2 drift lazily, as if there's nothing unseen tugging them. In a universe where dark matter is supposed to outweigh ordinary matter 5 to 1, this galaxy is effectively floating through space naked. Theories scramble to explain the anomaly. Could it have been stripped clean by a collision, some violent encounter ripping away its dark matter like a cosmic heist? Or is it a rare case of a galaxy forming without dark matter from the start, a celestial oddity born in conditions we've never witnessed? Skeptics argue it might be a trick of perspective, its distance fooling our measurements, but follow-up studies only deepen the mystery. Here's what truly unsettles scientists: if this galaxy isn't a fluke, it challenges the very foundations of how we think galaxies are built. Dark matter isn't just an add-on to our models, it's the scaffolding holding them up. Without it, entire theories of cosmic evolution might need reworking. Could there be other outliers like this hiding in plain sight? Every new observation of NGC 1052DF2 feels like staring at a broken puzzle piece, one that refuses to fit no matter how you turn it. Whether it's a cosmic exception or a crack in our understanding, this galaxy forces us to ask, do we really know how the universe builds its greatest structures? Or is dark matter's story far more complicated than we ever imagined? In October 2017, astronomers spotted an object streaking through our solar system that defied every expectation. Unlike the predictable comets and asteroids that originate from our own cosmic backyard, this visitor arrived on a trajectory so steep there was no doubt it came from beyond our sun's influence. They named it Oumuamua, Hawaiian for scout, and from the moment it was detected, it acted like nothing we'd ever seen. First, its shape, a bizarre, elongated cigar roughly 10 times longer than it was wide. Most space rocks are lumpy, irregular, but this looked almost crafted. Then there was its movement. As it swung past the sun, instead of slowing down as expected, it sped up slightly, just enough to raise eyebrows. Comets do this when their icy surfaces vaporize, creating jets of gas that push them along. Yet Oumuamua showed no tail, no coma, no visible outgassing at all. Theories exploded. Could it be a hydrogen iceberg, its invisible gas evaporating in the sun's warmth? Or perhaps a solid shard of nitrogen ice, chipped off a Pluto-like world in another star system? Both ideas fit some of the data, but they left gaps. Hydrogen ice shouldn't survive interstellar travel, and nitrogen would require an implausibly vast supply to chip off something so large. Then came the most provocative suggestion: could Oumuamua be something artificial? Harvard astrophysicist Avi Loeb famously floated the idea of a light sail, a thin, reflective probe propelled by starlight. The numbers almost lined up, but without definitive proof, the scientific community remained divided. The real frustration: we barely had time to look. By the time telescopes swung toward it, Oumuamua was already racing away, too faint and too fast to observe further. Was it just a strange but natural rock, shaped by processes we don't yet understand? Or did we catch a fleeting glimpse of something far more extraordinary, an artifact from another civilization, passing through like a ship in the cosmic night? One thing's certain: Oumuamua's brief visit shattered our assumptions about interstellar objects. Next time something like it arrives, and with newer surveys there will be a next time, we'll be ready. Until then, this cosmic scout remains an enigma, a silent visitor that left us with more questions than answers, and perhaps that's exactly what makes it so thrilling. Picture the universe just moments after the Big Bang, a seething cauldron of raw energy forging the first elements. Hydrogen and helium formed in abundance just as predicted. But there's a problem lurking in the cosmic ledger: lithium. If our models are correct, the early universe should have cooked up 3 times more lithium than we actually see today. It's like checking your bank statement and realizing a third of your money vanished without a trace. So where did all that lithium go? One theory points to stars not as factories but as cosmic sponges. As stars churn and burn, they might trap lithium deep in their cores, hiding it from our telescopes. Others suggest mysterious nuclear reactions in the early universe could have broken lithium apart before it had a chance to accumulate. But here's the catch: no known physics explains such a drastic shortage. Then there's the wild card: what if our understanding of the Big Bang's nuclear recipes is incomplete? Maybe exotic particles or undiscovered forces altered the delicate balance of element formation. Some researchers even speculate that lithium could have been eaten by hypothetical primordial black holes, vanishing into microscopic voids. Every time we measure ancient stars, the universe's fossil records, the lithium numbers come up short. It's a nagging discrepancy, a reminder that even our most trusted cosmic blueprints might be missing a page. Whether the answer lies in stellar secrets or new physics, one thing's clear. Until we solve this elemental mystery, the early universe's ledger won't add up. Tucked away in the constellation Bootes lies one of the universe's most baffling absences, a spherical void so staggeringly empty, it could swallow thousands of galaxies without a trace. Stretching 330 million light-years across, the Bootes void isn't just a gap in the cosmic web. It's a near-perfect sphere of nothingness, a great nothing that defies our expectations of how matter should be distributed. Most voids in space are like bubbles in foam, surrounded by filaments of galaxies. But this one, it's more like a cavern, vast and eerily hollow, with only a handful of lonely galaxies drifting through its expanse. How does something so empty even form? The leading theory suggests smaller voids merged over billions of years, like soap bubbles coalescing into one giant vacuum. But here's the catch: our simulations struggle to create a void this large and this sparse without invoking something unusual. Could dark energy, that mysterious force accelerating the universe's expansion, have stretched this region thinner than the rest? Or is it evidence of an ancient cosmic event, a collision with another universe perhaps, that swept the area clean? Then there's the unnerving possibility that the Bootes void isn't entirely empty. Some researchers speculate it might be filled with dark matter so diffuse our instruments can't detect it, or even rogue black holes drifting unseen. Others wonder if it's a statistical fluke, a 1 in a trillion chance that nature left this pocket of space untouched while filling the rest. But the real puzzle is what the void tells us about the universe's structure. If voids like this are more common than we thought, it could mean our models of cosmic evolution are missing a crucial piece. Every time we point telescopes at this cosmic desert, we're left staring into the abyss not just of space, but of our own understanding. Whether it's a quirk of physics or a sign of something deeper, Bootes' void challenges us to rethink how emptiness shapes the cosmos. If black holes are the universe's ultimate vacuum cleaners, sucking in everything that crosses their path, then white holes are their rebellious twins, cosmic fire hydrants blasting matter and energy outward with unstoppable force. At least that's what the math suggests. While black holes are very real, we've even photographed one, white holes remain purely theoretical, a ghost in the equations of general relativity. But here's the twist: their existence could rewrite some of the most violent events in the cosmos. Picture a black hole running in reverse. Instead of an event horizon trapping light forever, a white hole would have a no-entry boundary, a one-way door where matter erupts outward but nothing can ever get back in. Some theorists wonder if gamma-ray bursts, those fleeting but unimaginably powerful explosions in deep space, might be white holes briefly flickering to life. Others speculate they could be the other end of a black hole's tunnel, spewing out material into another universe through a wormhole. But there's a catch: white holes defy thermodynamics. They'd essentially create energy from nothing, violating one of physics' most sacred rules. That's why most scientists consider them mathematical curiosities, beautiful ideas with no proof. Yet the universe has surprised us before. Could white holes hide in plain sight, masquerading as unexplained cosmic flashes, or even the Big Bang itself? The debate isn't just academic. If white holes exist, they'd challenge our understanding of causality, time, and the very fabric of space-time. For now, they linger at the edge of theory, a tantalizing what if that keeps physicists questioning whether the cosmos has more tricks up its sleeve than we ever imagined. Among the faint glow of the cosmic microwave background, the oldest light in the universe, there's a patch so cold it shouldn't exist. Nestled in the constellation Eridanus, this anomaly stretches across a region of space nearly 1 billion light-years wide, its temperature dipping just slightly lower than the surrounding radiation. On its own, that might sound trivial, But paired with the gaping cosmic void lurking in the same spot, it becomes something far more unsettling. Could this be a scar from a collision with another universe? The cold spot was first spotted by satellites mapping the CMB's subtle temperature variations, a fossilized imprint of the universe's fiery infancy. Normally, these fluctuations are random, tiny ripples from quantum froth stretched across the cosmos. But this chill is too large, too focused, as if something drained energy from that patch of sky long ago. The leading explanation, a supervoid, an enormous, almost empty region of space might stretch between us and the cold spot. Light passing through such a void would lose energy like a ball rolling uphill, creating the temperature dip we observe. Yet even this doesn't fully account for the anomaly's size. That's where things get speculative. Some theorists propose this could be evidence of a cosmic crash, an encounter with a bubble universe in the multiverse's foam. Picture two soap bubbles brushing against each other, their surfaces briefly merging before recoiling. If our universe grazed another, the transfer of energy might have left behind a bruise, a cold spot where spacetime itself was stretched thin. Skeptics counter that the multiverse remains untestable, a dazzling idea without proof. But supporters argue the cold spot aligns eerily well with predictions of such collisions, making it one of the few potential fingerprints of a reality beyond our own. For now, the debate rages on. New radio surveys aim to map the void's true shape, while simulations test whether exotic physics like dark energy behaving oddly could mimic the effect. Whether it's a multiverse calling card or just a cosmic coincidence, the cold spot reminds us that even the oldest light in the sky can hold surprises. If it is a scar from another universe, what else might be hiding in the CMB's whispers? The answer could rewrite not just our place in the cosmos, but our understanding of existence itself. Beyond the icy reaches of Neptune, something unseen is stirring, tugging at distant objects with a gravitational whisper. Astronomers call it Planet 9, a hypothetical giant lurking in the frozen fringes of our solar system. The clues, a cluster of small, icy bodies orbiting in strange, tilted paths, as if an invisible hand is herding them. These objects don't just drift randomly. Their trajectories point to the presence of something massive, something hidden. The math suggests a planet roughly 5 to 10 times Earth's mass, tracing a stretched, looping orbit far beyond Pluto. If it exists, it would be a relic from the solar system's violent youth, a rogue world flung outward, now circling like a cosmic specter. But here's the catch: no one's actually seen it. The hunt has turned up empty, leaving researchers to wonder, could Planet 9 be something even stranger? Some speculate it might not be a planet at all. Could it be a primordial black hole, a grapefruit-sized knot of pure gravity left over from the Big Bang? Others suggest a captured rogue planet stolen from another star long ago. Skeptics argue the odd orbits might just be observational bias, a trick of limited data. Yet with each new discovery of a distant object moving unexpectedly, the case for Planet 9 grows stronger. Telescopes scan the outer darkness, probing for even the faintest glint of reflected sunlight or the telltale warp of gravitational lensing. The search is like looking for a lone street lamp in a foggy desert. Needle in a haystack doesn't even begin to cover it, but if or when we find it, the implications are staggering. A new planet, a black hole, either way, our solar system's map would need rewriting. What's out there pulling the strings of the Kuiper belt? The mystery endures, a reminder that even in our own cosmic backyard, the universe still has secrets to spill. Until we spot it, Planet 9 remains a tantalizing ghost, one that could reshape our understanding of home. Here's a thought that might keep you up tonight. What if reality itself changes when you look at it? Welcome to the quantum measurement problem, where the simple act of observation twists the universe into knots. At the tiniest scales, particles don't behave like billiard balls with fixed positions. Instead, they exist as a haze of possibilities, a superposition, until someone or something takes a measurement. Then, as if by magic, that fog of probabilities collapses into a single, concrete outcome. The implications are staggering. Does consciousness play a role in shaping reality? Some interpretations, like the famous Copenhagen view, suggest that measurement by an observer forces the system to choose a state. It's as if the moon isn't there until you glance up at the night sky. But others push back, arguing that hidden variables or parallel universes could explain the phenomenon without invoking human awareness. Maybe every possible outcome does happen, just in branching realities we can't see. Then there's the wild card, quantum decoherence. This theory sidesteps consciousness entirely, proposing that interactions with the environment, a stray photon, a whiff of air, cause the wave function to crumble on its own. No observer required, but even this leaves gaps. Why does a particle decide to land in one spot and not another? The debate isn't just physics, it's philosophy wearing a lab coat. If observation creates reality, where do we draw the line? Does a rat count as an observer, a camera, a single atom, the unsettling truth? After nearly a century, we still don't have a clean answer. Every interpretation has its flaws, its skeptics, its moments of pure bewilderment. One thing's certain, the quantum world refuses to play by the rules we know. Whether it's minds shaping matter or unseen forces guiding the dice, this riddle blurs the line between science and something far deeper. And until we crack it, the universe remains a place where the very act of looking changes what's there to be seen. Imagine the universe as a cosmic clock winding down with every tick, but what if it resets instead? This is the crux of the Tolman Paradox, a deep time riddle that pits two apocalyptic visions against each other. On one side, there's the grim specter of heat death, a future where the cosmos expands into an eternal, frozen graveyard, every star long extinguished. On the other, a cyclical universe where each Big Bang rises from the ashes of the last like a phoenix, carrying forward the entropy of its predecessor in an endless loop of rebirth. Richard Tolman's calculations in the early 20th century revealed something startling. If the universe does cycle, each new iteration would burn hotter and faster, like a fireworks finale on repeat. The reason, entropy, the universe's tendency toward disorder, would accumulate across cycles, shortening each subsequent lifespan. Picture a bouncing ball losing height with every rebound until it finally settles. But here's the twist. If the cycles persist, they'd leave faint echoes in the cosmic microwave background, subtle wrinkles we might one day detect. Yet the alternative, heat death, is no less unsettling. In this scenario, dark energy keeps stretching spacetime until galaxies vanish over the horizon, atoms unravel, and even black holes evaporate into whispers of radiation. Time itself could lose all meaning in a cold, silent void. The trouble is, both theories push beyond the limits of our current physics. To test them, we'd need to probe realms where quantum gravity and cosmology collide, maybe in the afterglow of gravitational waves from the universe's birth, or in the quantum fuzz at the edge of a singularity. Until then, the Tolman Paradox lingers, a fork in the road at the end of time. One thing's certain, whether the universe is a one-act tragedy or an endless encore, the answer will rewrite not just our fate but our understanding of existence itself. And that's a paradox worth losing sleep over. Watch a galaxy spin and you'll notice something strange. Its outer stars whiz around far faster than they should. According to Newton's laws, stars on the edges of galaxies, like our own Milky Way, ought to slow down as they orbit, much like planets farther from the Sun move more sluggishly. But that's not what happens. Instead, these stars race along at breakneck speeds, as if gripped by some invisible hand. This cosmic mismatch is the galaxy rotation problem, and it's one of the strongest hints that our universe is filled with something we can't see. Enter dark matter, the elusive substance that doesn't emit, absorb, or reflect light, yet exerts enough gravitational pull to keep those speeding stars from flying off into the void. For decades, this explanation has dominated astrophysics, painting dark matter as the hidden scaffolding that holds galaxies together. But there's a twist: not everyone is convinced. Modified Newtonian dynamics, or MUND, proposes an alternative. What if gravity itself behaves differently on galactic scales, growing stronger where Newton's equations predict it should fade? The debate cuts to the core of physics itself. Dark matter supporters point to smoking guns like gravitational lensing, the way massive clusters bend light around them more than visible matter alone can explain. Yet MUND proponents argue their tweaked version of gravity can predict galactic rotations with surprising accuracy. No invisible particles required. The stakes couldn't be higher. If dark matter is real, we're missing nearly 85% of the universe's mass. If MUND is right, we may need to rewrite the rules of gravity itself. For now, the mystery endures. New observations of ultra-diffuse galaxies, ghostly systems that seem to lack dark matter entirely, only deepen the puzzle. Are these outliers proof of MUND, or just cosmic oddities that dark matter can still explain? Every telescope trained on the heavens brings us closer to an answer, but one thing's certain: the way galaxies spin isn't just a quirk. It's a revolution in the making, forcing us to rethink the fabric of reality. Amid the swirling chaos of dying stars, one nebula stands out for its unnerving perfection: the Red Rectangle. Floating 2,300 light-years away in the constellation Monoceros, this cosmic gem doesn't billow like a typical stellar furnace. Instead, it forms a near-perfect X shape, as if etched into the heavens with a ruler and compass. Most dying stars expel their outer layers in ragged, asymmetrical bursts, so what created this eerie symmetry? The leading suspect, a pair of aging stars locked in a gravitational waltz. At the system's heart, a binary duo may be sculpting the nebula's structure, their interactions channeling dust and gas into those precise, intersecting beams. One star, a red giant, sheds its outer layers while its smaller companion funnels the material outward in opposing jets. Like cosmic gardeners pruning a celestial hedge, their dance could explain the nebula's sharp angles. Yet mysteries linger. The red rectangle's vibrant crimson hue, unusual even among nebulae, comes from complex carbon-rich molecules scattering light. Some researchers speculate these very molecules, forged in the chaos of stellar decay, might be the building blocks of life elsewhere in the universe. Could this geometric marvel double as a factory for organic chemistry? But here's the kicker: recent observations reveal finer structures within the nebula, delicate ladder like rungs stretching across its arms. These nested patterns defy even binary star models, hinting at forces we don't yet understand. Some theorists wonder if magnetic fields, spiraling like invisible threads, are guiding the chaos into order. Others suggest outflows from the stars might pulse in rhythmic bursts, stacking layer upon layer like a cosmic fingerprint. Whether it's stellar choreography or hidden physics at work, the Red Rectangle challenges our assumptions about how stars die. Most leave behind chaotic clouds. This one leaves a puzzle box, and as we study its precise, almost artificial geometry, we're reminded the universe doesn't just create chaos. Sometimes it crafts with uncanny precision. Picture a civilization so advanced they've tapped into the raw power of their sun, encasing it in a colossal energy-harvesting shell. It sounds like science fiction, but this is the essence of a Dyson sphere, a hypothetical megastructure imagined by physicist Freeman Dyson in the 1960s. The idea is simple but staggering. A super-advanced society might build a vast network of solar collectors around their star, capturing nearly all its energy to fuel their expansion across the cosmos. While no confirmed Dyson sphere has been found, astronomers have scoured the skies for clues stars that flicker in unnatural ways or glow with unusual infrared signatures, hinting at structures blocking their light or re-radiating absorbed energy. Tabby's star, with its erratic dimming, remains the most famous candidate, but here's the twist: despite years of scrutiny, every potential megastructure signal so far has turned out to have a natural explanation: cosmic dust, swarms of comets, or exotic stellar physics. That hasn't stopped the hunt. Some researchers argue we might be looking for the wrong thing. Instead of a solid shell, an advanced civilization might build a Dyson swarm, a fleet of energy-harvesting satellites orbiting their star in dense formation, leaving gaps that could explain irregular dimming. Others suggest we should search for waste heat, the faint infrared glow of energy being used on an unimaginable scale. But the deeper question remains: if these structures are possible, why haven't we found definitive proof? One answer lies in the sheer scale of time and space. Even a galaxy teeming with intelligent life might have only a handful of civilizations building megastructures at any given moment, and spotting them across billions of stars is like searching for a single lighthouse in an ocean of darkness. Yet the pursuit is far from futile. Whether or not alien megastructures exist, the search pushes our technology forward, refining how we study distant stars and interpret their mysteries. Every unexplained flicker, every anomalous heat signature forces us to ask: are we alone, or is the universe hiding architects greater than we've ever imagined? The answer may not come in our lifetimes, or it could arrive tomorrow, hidden in the next batch of telescope data, and that possibility alone makes the search worth it. Deep in the heart of every star, beneath the crushing weight of nuclear fires, trillions of ghostly particles slip unnoticed through matter, as if it weren't even there. These are neutrinos, the universe's most elusive travelers, passing through planets, through your body, through everything without a trace. For decades, scientists assumed they were weightless phantoms, but then came the bombshell. Neutrinos change identity as they race through space, morphing between three distinct flavors, and that shimmering act, it's only possible if they carry mass. Here's the puzzle: neutrinos are shockingly, impossibly light, while an electron, the next lightest particle, tips the scales at a measurable fraction of an atom. Neutrinos are billions of times lighter. They shouldn't be. According to the Standard Model, our best blueprint for particle physics, mass comes from interactions with the Higgs field. But neutrinos flirt with the rules. They're far too light for that mechanism alone. It's like finding a feather that somehow defies gravity, floating just a whisper above the ground. Theories abound. Some suggest neutrinos might be Majorana particles, their own antimatter twins with masses emerging from entirely new quantum processes. Others propose they're messengers from higher dimensions, their true heft diluted as they cross into our reality. The wildest idea, that their feather-like masses hint at an undiscovered type of Higgs field, one that operates on scales we've yet to probe. Every experiment designed to weigh these phantoms, from detectors buried in Antarctic ice to vats of liquid xenon deep underground, only deepens the mystery. Their masses are so small, our tools strain to measure them, yet the stakes couldn't be higher. Crack the neutrino mass puzzle, and we might unlock doorways to physics beyond the Standard Model, perhaps even clues to why matter triumphed over antimatter in the early universe. For now, neutrinos remain cosmic enigmas, particles so light they barely exist, yet heavy enough to shake the foundations of physics. And until we solve their riddle, they'll keep slipping through our grasp quietly, endlessly, rewriting the rules as they go. Galaxies are like snowflakes. No two look exactly alike, yet they fall into familiar categories. spirals with their elegant arms, ellipticals like cosmic footballs, and irregulars with their chaotic beauty, all seem to follow a hidden rulebook called the Hubble sequence. But who or what wrote those rules? One clue lies in their birthplaces. Galaxies forged in dense regions of the early universe often grow into orderly spirals, their delicate shapes sculpted by the gentle tug of dark matter. Those born in cosmic traffic jams where collisions run rampant tend to mash into elliptical, smooth, featureless giants where stars swarm in every direction. Yet even this tidy story has cracks. Some galaxies defy expectations, like the ultra-diffuse ones that drift like ghosts, barely held together by gravity at all. Then there's dark matter's invisible hand. Simulations show its gravitational web acts like a cosmic puppet master, guiding galaxies into their molds over billions of years. Without it, spirals wouldn't spin so gracefully and ellipticals wouldn't cluster so predictably. But why do some galaxies resist the pattern, staying irregular despite the universe's best efforts? Perhaps the answer lies in their violent histories. A single collision can rip a spiral's arms apart or trigger a burst of star formation that reshapes it entirely. Even our Milky Way isn't finished. Its fate is a slow dance with the approaching Andromeda Galaxy, a future merger that will rewrite its story. The Hubble sequence isn't just a classification, it's a crime scene, and every galaxy holds clues. Whether it's dark matter's whisper, ancient collisions, or some deeper physics we've yet to uncover, one thing's clear: the universe has a flair for order even in chaos. And decoding these patterns might just reveal how galaxies and we came to be. High above our heads, invisible bullets streak through the cosmos, cosmic rays, carrying energies that dwarf anything humanity's most powerful particle accelerators can produce. Most come from familiar sources, exploding stars, churning magnetic fields, but a rare few defy all logic, packing so much punch they shouldn't exist. These are ultra-high-energy cosmic rays, particles screaming through space with the force of a fastball crammed into a single proton, millions of times more powerful than anything the Large Hadron Collider can muster. And here's the kicker: we have no idea what's slinging them at us. The math just doesn't add up. For a particle to reach these extreme energies, it needs an accelerator of cosmic proportions, something with gravitational or electromagnetic muscle beyond anything in our galactic neighborhood. Even supernova, nature's most violent explosions, fall short. So what cosmic cannon is firing these subatomic bullets? One leading suspect: supermassive black holes in distant active galaxies. Their swirling accretion disks acting like natural particle colliders, hurling matter across the universe with terrifying force. Others point to rarer cataclysms colliding galaxy clusters, or perhaps even the annihilation of hypothetical dark matter particles, releasing bursts of energy we're only beginning to comprehend. Then there's the mystery of their journey. These rays should be crippled by the cosmic microwave background, the faint radiation left over from the Big Bang. Over vast distances, protons at these energies ought to collide with photons, draining their strength long before reaching Earth. Yet somehow they arrive almost unscathed. Are they coming from closer than we think, or is something shielding them en route, bending the rules we thought were set in stone? Every detection sends physicists scrambling. Arrays of sensors sprawled across deserts capture these rare impacts, tracing their paths backward only to find voids, empty stretches of space where no known power source lurks. It's as if the universe is thumbing its nose at us, flinging impossibly energetic particles from the cosmic equivalent of a dark alley. Whether it's hidden black holes, exotic physics, or something entirely unseen, one thing's clear: the answers won't just rewrite astrophysics. They'll reveal the universe's most extreme particle accelerators, lurking in the shadows, waiting to be discovered. Imagine every choice you've ever made, every path taken or ignored, spawning a new universe where the opposite happened. That's the multiverse in its most dizzying form, an infinite tapestry of realities, each with its own laws, constants, and perhaps even versions of you. The idea didn't spring from science fiction, though. It grew out of inflation theory, the leading explanation for the Big Bang's explosive beginnings. If space expanded faster than light in those first moments, tiny quantum fluctuations could have been stretched into cosmic proportions, creating isolated pockets, bubble universes, where physics itself plays by different rules. The appeal is obvious. A multiverse could explain why our universe seems oddly fine-tuned for life. If countless realities exist with random physical constants, it's no surprise we find ourselves in one where conditions allow galaxies, planets, and us. But here's the catch, proving it. By definition, other universes would lie beyond our cosmic horizon, forever out of reach. No signal, no light, no matter could cross the void between them. That leaves scientists wrestling with a thorny question. Can an idea be scientific if it's fundamentally untestable? Skeptics argue the multiverse veers into philosophy, a comforting story with no empirical teeth. Supporters counter that clues might lurk in the cosmic microwave background. Anomalies like the cold spot could be bruises from collisions with other bubbles. Others hunt for signatures in gravitational waves, relics from inflation's aftermath. But even if we found such hints, they'd still be circumstantial, a fingerprint without a hand. The debate cuts deeper than cosmology. It forces us to ask what science is. Must every theory be falsifiable, or can some remain compelling possibilities waiting for future breakthroughs? For now, the multiverse remains a dazzling, maybe a hypothesis that reshapes how we see reality, even as it eludes proof. Whether it's the next revolution or a dead end, one thing's certain. The mere possibility of infinite universes reminds us how little we truly grasp about existence and how much wonder still waits in the unknown. These cosmic puzzles, from dark matter's invisible scaffolding to the eerie absence of alien signals, aren't just gaps in our knowledge, they're doorways. Each unanswered question peels back another layer of reality, exposing just how much we don't know. And isn't that exhilarating? Think about it. Every time we solve one mystery, the universe hands us 10 more. The more powerful our telescopes, the stranger the cosmos becomes. The deeper we dig into quantum foam or galactic voids, the clearer it gets. We're just scratching the surface. But here's the beautiful part, the pursuit doesn't end. Every generation builds on the last, turning yesterday's impossibilities into today's textbooks. Those flickers of curiosity, why do stars spin too fast? What carved the Kuiper Cliff? Propel us forward, reminding us that wonder is the engine of discovery. So keep looking up. The next breakthrough might come from a lone researcher staring at data at 3 a.m. or a telescope catching a glint no one expected. The universe isn't done surprising us, and honestly, that's the best part. What cosmic riddle fascinates you the most? Drop your thoughts below, and if you're hungry for more mysteries, hit subscribe. The cosmos has plenty of secrets left to share.